So last class we talked about angular momentum, and we said that our goal was eventually to solve the Schrodinger equation for the hydrogen atom. And we wanted to talk about angular momentum in relation to that because the hydrogen atom is spherically symmetric, and angular momentum should be a good quantum number, and it should simplify our equations considerably. Also, the potential for the electron in the hydrogen atom, it only depends on its distance from the nucleus. It does not depend upon the angle. So it should be possible to separate out its wave function as a product of the angular part and the radial part. And that is what we're aiming at. And we started in a slightly different way. That is, we started looking for simultaneous eigenstates of the angular momentum and the Hamiltonian. So that is what we are looking for to make it easier for us to find the form of the functions and solve the equation. In angular momentum, as such, we found that the three components of angular momentum cannot be obtained simultaneously for any system, and only one of them can be determined when the other two are unknown. And it could be any of them, but since according to the choice of our coordinate system, LZ turned out to be the simplest, everyone chooses LZ, and so did we. We found the commutators of the various components of angular momentum, and we also found that the L square operator that commutes with separately with Lx, Ly, and Lz. So we could narrow down our search even further to simultaneous eigenstates of L square and L and the Hamiltonian when we want to solve for the hydrogen atom. Then we then we found some properties of the. No, we converted the angular momentum operators into their form in the spherical coordinate system, because that is what we will use to solve the hydrogen atom. Okay. And we wrote down Lx, Ly, Lz, and L square. So today we will actually do the solution for the simultaneous eigenstates of L square and Lz. So what are the equations? So we want to write we want to find out simultaneous eigenstates of Lz and L square. Okay. And once we do that, in this subset, we will then look for the solutions for the radial part of the hydrogen atom wave function. So what are the two equations? The first equation is the the eigenvalue equation for Lz. And this wave function, I am saying, is a function of two quantities, L and M. These are indices. So M refers to the eigenvalues of the Lz operator and L to the eigenvalues of L square operator. And this psi will depend on both these quantities. So let's say what is psi? So psi Lm is basically a function of theta and phi. Phi is the angle with the z-axis and theta is the angle with the x-axis. If you remember the picture from before. This one. So, sorry, phi is the angle with the x-axis and theta is the angle with the z-axis. Did I do the reverse? No, this is fine. Okay. So, let us see. So Lz acting on psi Lm, this will give me an eigenvalue, which I am calling H cross M, psi Lm. And the second one is the L square operator, which is acting on psi Lm, to give me H cross square some number lambda psi Lm. Now I have included the constant H cross in the equation for Lz because it has the same unit as angular momentum, which will make my M dimensionless. Also, L square has units of H cross square, so lambda will be dimensionless. That will help me when I solve the equations. And M belongs to real numbers in general because this is an eigenvalue. Okay. And similarly, lambda also belongs to the set of real numbers. Okay. Also, since this is a squared operator, lambda is positive.
Is it lambda or is it L? Because you said L is indicating the L square operator, right?
Yeah, I will write it in terms of L. So this lambda has to be positive. Okay. And then I will write lambda as L into L plus 1. Now, why am I doing this? So typically, if you know that lambda is real and lambda is positive, you would write it as L square maybe to ensure that it's always positive. But this is again a wise after the event step, because this, if you write it as L into L plus 1, then the differential equation that you get, that has a standard form and the solutions were known from 100 years ago. So that is why instead of writing lambda just as maybe L square like we've been doing before, when we wanted to ensure that the eigenvalues are, we're just looking for the positive ones and we don't complicate things unnecessarily, we will take L into L plus 1. Now, if it is L into L plus 1, I can draw the values of lambda versus L. Okay. Then the function L into L plus 1, that looks like this. Okay, this is the L into L plus 1 function. And then for every value of lambda, you have two values of L. And one is negative and one is positive typically. But we will only be looking for the positive values of L, because that is sufficient, because what we need is the value of lambda, and since both these L's will give me the same lambda, I can choose either one. Okay. So we'll only be looking for positive values of L. And then in general, L also belongs to real numbers for lambda greater than 0. Okay. And with this set of L, I can cover all possible values of positive lambda. Okay. So after I say that, I will start solving the first one. So the first solution, first equation that I want to solve is Lz acting on psi Lm gives H cross M psi Lm. This is a pretty simple equation to solve. So the Lz operator is H cross by I del del phi, and then you have psi Lm and H cross M psi Lm, and I can delete H cross. I have then del psi Lm by psi Lm. This is equal to I m del phi. Okay. I can integrate this to give me ln psi lm equal to im phi plus some function of theta, because remember psi is a function of both theta and phi. Okay. And then I can write psi lm theta phi as e to the power im phi and e to the power c theta. And this I can simplify or just change the notation a little bit and say this is plm theta. Okay, so this is the solution of the differential equation. For normalization, okay, let's
Ma'am,
say,
what is
yeah.
the P here?
What is what?
What is the PP here? I mean, what is it
Oh,
denoting?
it's just this e to the power c theta.
Okay. So it doesn't have any sort of a significance. We're just replacing the variable.
Yeah, we are just replacing e to the power c theta as plm theta.
Okay.
And we'll find this function directly instead of c later on. And for normalization, we can add a additional factor n lm e to the power im phi plm theta if we want to. Okay, if we want to. Otherwise, we can include it inside the plm theta as well. Now, what we have found out is the form of the wave function. We don't yet know the eigenvalue. We've just said it's m, but we don't know anything about m. Now here, since this is not a particular system, you don't get an explicit expression for m. What you will get is the form of the solution or certain restrictions on m, right? So this is not the Schrodinger equation. If it was a Schrodinger equation, the eigenvalues would give you the energy of whatever model system you were studying. So here you need to look at the general physical properties of the operator. Well, I shouldn't say physical properties, but just properties of the operator, not of the physical system. So what do we know about LZ, or what other things can be imposed to find out some restrictions on n? One is that the wave, since we are dealing with a wave function, it must be single valued, meaning at an angle of phi and an angle of phi plus 2 phi, since the wave function is the same, the value of Lz should be the same. Sorry. So what we're demanding is a rotational symmetry. Okay. And if we demand rotational symmetry, then what we are mathematically asking is that psi lm theta phi plus 2 pi, that should be equal to psi lm theta phi. Okay. Using this, I can write e to the power im phi plus 2 pi is equal to e to the power im phi. Okay. And e to the power im phi into e to the power im 2 pi is equal to e to the power im phi. So e to the power im 2 pi is equal to 1. And we know that this holds true if m is an integer. This is true if m is an integer. right? So this is a mathematical identity that we know. So what we found out is now something more about M. That M, we had chosen it to be any real number, but now we know that it is a integer. And that is all that we can know about M at this moment. When we solve for the hydrogen atom, then we will find how, like that actual values of M, what it can be for the hydrogen atom. If we solve another system, this, yeah?
Ma'am, I didn't quite understand why the fact that the wave function is single valued corresponds to some kind of rotational symmetry. Can you explain why? I did not understand that.
Oh, so this phi is a rotation about an axis, right? So after a 360-degree rotation of the wave function, it should be the same wave function. That is why. So its properties should be the same, which means that the value of Lz should be the same. Because a 360-degree rotation is an identity operation, right? That's why.
Okay.
Now, when we just say that just solve the eigenvalue equation for Lz, the equation doesn't know that this is a this is a three-dimensional system or what we are dealing with. So this is an additional information that we have that the equation doesn't have. And when we use that information, then we find that okay, now M is not it's not real, but it is a subset. It is an integer. It has to be if the wave function has to remain the same under 360-degree rotation. Get it? It's not a. I mean, it's a very.
Ma'am, so you're saying at each point of 3D space, there is a definite value of psi. So if we substitute phi plus 2 pi, we are arriving at the same point. So it should correspond to the same value as it was.
Yeah. Exactly. Since it is the same point in space.
Okay, so ma'am, we can assume this because we are initially assuming that the wave function itself is spherically symmetric. So.
No, it has nothing to do with spherical symmetry. Even if it was a very, very distorted system, a 360-degree rotation will still give you back the same system.
Okay, ma'am. Yeah.
Yeah. So where this matters is like for mathematical functions, they don't know that it's 3D, right? It could be 4D, 5D, whatever. So in that case, you would not be able to use such a condition. But here, since we are dealing with a physical wave function, that is why this is an additional constraint that we have. And that tells me, like, give me a subset of M. It still doesn't give me the values of M. That will depend on the system that we are studying. Now, that can be the hydrogen atom, that can be the hydrogen molecule, it can be the uranium, fluoride molecule or something. Those all have different symmetries, but this condition is still true. Because the space is 3D and 360-degree rotation gives you the same thing, always. Okay, so this was a simple equation to solve. Now we come to the L square, which is a little bit more work, but it's not difficult. So psi Lm is equal to square L. Just one. Psi Lm. Now we want to solve this. I will just write the L square operator. Theta. Theta. Theta 1 by sine square theta del square del phi square. Okay. And m this is equal to h cross this one psi Lm. the equation we want to solve. Okay. Cancel h cross square. And now I know a little bit more about theta phi. I know that it is e to the power m phi p ln theta. So this last term is simpler. So the first thing let's do is del square del phi square psi ln. Okay, so this is I m whole square e to the power I m phi p ln theta. That is minus m square psi. Fine. Then we'll do the rest of it. So the rest of it is now minus sine theta, del theta, sine theta, del b del theta, phi, and I have minus of del square del phi, so minus of 1 by sine.
Ma'am, could you scroll up a little?
Is that fine?
Yeah, ma'am, just 1 minute.
One more. Okay. Minus m square psi ln. Okay. This is equal to L into L plus 1. Done?
Yes, ma'am.
Okay. Now what I can do is I can multiply minus sine square. Multiply minus sine square theta. So then I get a sine theta del theta on sine theta del p ln del theta. I could have also actually deleted. Okay, so I'll write first m phi. Then from the second term I have minus then m square e to the power I m phi p ln, and I have minus sine square theta L into L plus 1 e to the power I m phi p ln. Okay. So I can delete e to the power I m phi as well. I could have done that earlier. I didn't notice. Okay. So this, I can bring everything now to the left side to get my final equation. So sine theta del theta, sine theta del del theta. Okay. And then we have plus plus 1 sine square theta minus m square p ln equal to 0. Okay, so now we have reduced the equation to a differential equation only in theta, and we only need to determine now the PLM part of the wave function from this equation. Now, if we change the variable to cos theta, then this equation gets simplified. So the thing is, writing a function of theta as a function of cos theta is always possible. It's only the range of values of the function that changes. So, and also here, our range of theta is basically 0 to pi, which corresponds to a range of cos theta from -1 to +1. And all points are mapped 1 to 1, theta to cos theta. So there is nothing wrong in converting a function PLM theta to a function of cos theta. And that is what we will do. We will define a new variable as x as cos theta, okay, and change all the operators and all the variables in this equation. So a ddx then is basically -1 by sine theta dd theta is then minus sine theta dd. And what we need is, and the main differential operator here is basically sine theta dd theta, and we have two of them. So sine theta dd theta is then sine theta minus sine theta ddx, and this is minus sine squared theta, which is cos squared theta minus 1 ddx, and cos theta is x, so this is x squared minus 1 ddx. So we have got the form of sine theta dd theta in terms of x. Okay. Now using this in the equation, we will replace these two operators with x squared minus 1. So we get an x squared minus 1. And then we have a wait 1 minute. So this is this x squared minus 1 ddx. And then we have x squared minus 1 ddx of PLM. And the second term remains almost the same. Plus 1 minus x squared minus m squared PLM equal to 0. Okay. Now changing the sign of all terms. Now I'm going towards the standard form of the differential equation whose solution we know. So why I am doing this is to get to that form. So I'm changing the sign of all the terms. So in the first term, I'm just doing 1 minus x squared here. So 1 minus x squared ddx. Okay, no, I'll change the sign of this. Keep this like this. And this one also I am changing this to 1 minus x squared then I have a minus m square. Zero. Then I
Ma'am, don't we need to put a minus sign?
wait, did I make a mistake? Oh yeah, this one will be a plus. Yeah, now I think it's fine. So I changed the sign of this one, changed the sign of, oh no, I should put a minus sign. Okay. Now it's fine. Change the sign here, and I changed the sign here. Okay. And then I divide throughout by 1 minus x. Okay, let me see if I can just do it in one step. So all I want to do is, I want to have 1 minus x square everywhere instead of x square minus 1. That's my goal, basically. Okay, so if I divide throughout by x square minus 1, then I have dx 1 minus x square dx. Okay. Then here, in this term, my minus sign goes away. So L into L plus 1 minus x square. I'm dividing by x square minus 1. So I can write this as m squared by 1 minus x squared. Okay. Okay. So this is what I want, basically. Now, when I
Ma'am, the 1 minus x square will get cancelled out, right, when you're dividing?
yeah. Thank you. Thank you. Yeah. So this is the form that I want, because there is a standard equation from 100 years ago called the Legendre Equation. Yeah, the pronunciation is probably something like Legendre or something, but I'll just stick to Legendre, because better to just say it as wrong as you want rather than halfway right and halfway wrong. So this is the Legendre Equation, and this has this form. Zero. So this is what is called the Legendre equation, and when x lies between minus 1 and plus 1, and n is an integer. Yeah. So this is what was known, and this looks almost like this. We just have a little bit of a difference still. So we will try to get it as close as possible to this form of equation. So what can we do? We see that this 2x term is missing, but we have a ddx here, so we will get a 2x from the x square, which means that we should solve that part. So I have 1 minus x square, then d square dx square plm, and minus dplm dx. I'll just put it here. I'm sure you're smart enough to do that. So minus 2x dplm dx. And in this part, I have 1 extra term. This is this m square by 1 minus x square. So this part is extra. So we don't know the solution of the equation when we have the m square term, but we know it when this m square term is missing, is not there. Okay. So what we'll do is we will solve it for m equal to 0. So this will be part of the solution, but let's go step by step. So when m is equal to 0, our equation looks exactly like the Legendre equation. So let's get back, which means that the solutions of the Legendre equation are useful for us when m is 0. So we will, let's see what the solutions look like then. So which should be similar to our solutions.
We can substitute a power series, right, to find out the solution when m is equal to 0.
Yes, we will use the power series solution. Yeah.
No, like
But that-
we did it for the harmonic oscillator. So the exact same way the equation is very similar looking, right?
Yeah, so we will get something quite similar. Yeah, we will get something quite similar. But remember, even in the harmonic oscillator, when you substituted the power series, what you got was a recursion relation. There were still some
Yes.
unknowns. Yeah, the first two, the A0 and A1, the first two coefficients were unknown. So those two have to be determined from this Legendre solution, just like we got for the Hermite functions. So it's quite similar, the two solutions. Just slightly the functions like the Hermite functions and the Legendre functions, they're different, but the procedure is almost the same. And you'll see even more similarities as I continue. So the Legendre equation solutions, what do they look like? So they say that the solution for yx has two parts which are independent, y1 and y2, and a0 and a1 are arbitrary constants. Okay. And the functions themselves are, so y1x, no, let me see. So here also there are two subsets of solutions, since there are two functions. Case 1 is when n is equal to 0 or n is equal to 2m, which means basically the even solutions. Then y1x is equal to 1 minus 3x squared, 1 minus 10x squared plus 1 minus 10x squared, 35 by 3x to the power 4, and so on. So these functions are known, the solutions. And case 2 is when we have odd solutions, that is y2x is equal to x minus 5 by 3 x cubed, x minus 14 by 3 x cubed plus 21 by 5 x to the power 5, etc. So you see
How
why
are we getting these solutions?
these solutions were already determined by Legendre from the like I said 100 years back. So you can Okay, I'll show you. Once we get the recursion relation, I can show you how to verify that. Okay.
Oh, so
At
we are
the-
not finding these out here.
No. We are not finding them right now. I'm just
Okay,
telling
these are
you
there
the-
with us. Okay.
Yeah. I'm just telling you the solutions. Then I will show you that. I will show you actually how these are coming, but for now I haven't done it yet. So okay, so these are the things. These are the solutions that were known, and so PLM will probably have solutions that look like this. Now the funny part of Legendre solutions is that their normalization is a bit funny. So what the mathematicians wanted was that, okay, no, I will not close the brackets. So what they wanted was that the solution of that every function, if you put x equal to 1, the value of the polynomial should be 1. So what they wanted was that y of, let's say y1 of 1 is equal to 1. Okay. Or y2 of 1 is equal to 1. So this is what they wanted. Okay. This is what is called the normalization of Legendre polynomials, which means that in general the normalization condition for these polynomials looks also a bit different from what we know. So it is an integration from -1 to 1 of okay, so let me call these the normalized ones. I'll call them P, okay, similar to R. So these are the normalized ones. The Y's are not normalized. So this will be, let's say, Pi x Pj x dx is equal to 2 by 2n plus 1 delta ij. So the normalized Legendre polynomials, they should obey this normalization condition. So you see, so when so if the two Legendre polynomials are different, so they correspond to different values of n, then they will be orthogonal because of the delta function. And if they are the same, their overlap will be 2 by 2n plus 1. And then you divide, of course, by the square root of this number to get the normalized Legendre function. And the normalized Legendre functions, they have the form or this is the, you can say this is the generalized expression for the Legendre, normalized Legendre functions of Legendre polynomials. This is a general form for any of them. So here I've written a few examples for y which are not normalized. So these come directly from the recursion relations. And when you normalize them with this sort of strange condition, and then you get normalized Legendre polynomials which obey this sort of, you can call it a generating function, I believe, but I'm not that good mathematically. Probably this is what is called a generating function. But this is the Rodriguez formula for Legendre polynomials. So we had a Rodriguez formula for Hermite polynomials as well. This is the one for the Legendre polynomials. And they will give you the normalized Legendre polynomials. And what do they look like? So some values. So P0 x is 1, P1x is x, P2x is half 3x squared minus 1, and so on. Fine. So this is just like a sort of mathematical interlude about Legendre polynomials. Now we will go back to like, I don't know the name, but someone was saying we can use a power series solution. Yes, we can do that. And that is what we will do to get the recursion relation. Where were we? Back to the solution. Solving the L square equation for m equal to 0.
Ma'am, can you just scroll a bit?
Yeah.
Thank you, ma'am.
Okay. So this I should have written. I should have written i's all over here, not L. 2 to the power I factorial ddxi squared minus. Okay. So ddx of, now we have, so this is the equation that we want to solve. Now since we've set m to 0, we don't need to write m anymore. So I'll just write PL. This will also help us distinguish between the situation when we have a solution for m equal to 0 and m equal to some other number. And then we use a power series for this. So here we don't have any boundary conditions per se. So in the harmonic oscillator, we had obtained this extra exponential factor which we multiplied with the power series solution. But here we'll just go with a general power series. Whatever you like. Okay. And we substitute now this solution in our differential equation. And what we get is 1 minus x square ddx infinity k x to the power k. Okay. Then plus 1 sum k to 0. Okay. So now I just have to sit and solve this. So now I pick coefficients of x to the power k. So from the first term, I get x to the power k when k is equal to k plus 2. Right? So I will get a k plus 2, k plus 2, k plus 1. Then in the next one, it's already x to the power k. So I just have a k minus 1. From the third term, I have minus 2 akk. And from the fourth term, I have L into L plus 1. This already looks like a recursion relation. I'll just make it a little bit prettier. So ak plus 2 plus 2 into k plus 1. I can take ak common from the three terms. So I have ak. Okay, I'll just do it in 2 steps. Better. So I take plus k common. K minus 1. Did I make a mistake? Oh, what? I had a minus here, sorry. This is a minus. Minus. K minus 1 plus 2, so k plus 1. This is my recursion relation. I can put the AK is inside it. So similar to what we got for the harmonic oscillator, we get a recursion relation for the coefficients of the various powers of x in our power series solution. Now we need to again think a little bit. So this directly means that all the even powers of x club together. So if you have a0, then from a0 you can get a2, a4, a6, etc. And this will give you a polynomial solution. Then if you have a1 and you get a1, a3, a5, you can obtain the values and you get another polynomial solution involving the odd powers of x. And in general, the solution is a linear combination of both. Now, we have to think again of the wave function. Now, this variable in our wave function is cos theta. Okay. And it goes from +1 to -1, the value of cos theta. In between, it is less than 1. So, and in the power series solution then, at the points where x is equal to 1 or -1, the series does not converge. It will diverge because it's an if this is an infinite series. So where did I write the solution? Power series solution. Oh, here. So in this expansion, if k really goes up to infinity, then at points where x is equal to 1 or x is equal to minus 1, the value of this polynomial will be infinity, which means that I will have a divergent solution, okay, or a wave function, a point in the wave function which will have a value of infinity. Now this cannot correspond to a wave function for a particle, because such a wave function will not be normalizable. So what is the solution? The solution is that this must be a truncating series. This is the same argument as in harmonic oscillator, only slightly different. So there the wave function, the full wave function was diverging. Here there are 2 points in the wave function when x is equal to +1 or -1, which will diverge. But that will make the whole wave function diverge anyway, because the wave function is for the full range of x values. So to avoid that, our physical wave functions cannot diverge at any point, but the power series will do so for x equal to 1 or -1 if the series does not truncate. And when will the series truncate? The series will truncate when k into k plus 1 is equal to L into L plus 1 for a given value of L. So L is a parameter in the original equation, right? So the solution for a given value of L will only have powers up to k, where k into k plus 1 is equal to L into L plus 1. So this will be k max, let's say. Okay. This also means that since k is an integer, L will have to be an integer. This also means that since k is an integer, L also belongs to integers. Now, we had initially assumed that L could be real. In our the equation we got from quantum mechanics, but valid solutions can only be, you can only get normalizable valid solutions for L being an integer. Okay. This is the, okay, fine. This is okay. But L is also an integer. Therefore, L is equal to 0, 1, 2, 3, etc. This is again a very important implication, which means that L squared only has integer eigenvalues. Now this is
But it is not directly obvious to me, because we have L into L plus 1 equal to some integer. So you are saying from this directly we can say L has to be an integer.
No, so K's are always integers.
Yes, so LHS is an integer, but the RHS is L into L plus 1. So
So as soon as L is not an integer, it will never be equal to any K. And then you'll have a divergent solution.
okay.
So unless L is an integer, it is not guaranteed that the series will truncate.
Yes, ma'am, but I was talking about the opposite, that you are saying that that implies that it is an integer. I mean, if it is an integer, then it is guaranteed, but if it's not, then can't there be cases where it is still equal to an integer on the left hand side?
There will be, yes. If it is not an integer, then there will be cases where it will be equal. But then anyhow, if you have a real number which becomes equal to k, I mean, whether you call it a real or integer, the value is an integer, right?
No, ma'am, I'm saying
as
that
soon as it's equal.
L can be some non-integer such that L into L plus 1 gives K into K plus 1. I mean,
No, that is not. Is that possible? I don't think so. I don't think that is possible. I mean, this L into L plus 1 is equal to K into K plus 1. That is either L equal to, I think it's only L equal to K that will give you that answer. It will never convert. So K into K plus 1 is also an integer. And if
yes.
L is not an integer, then L into L plus 1 will never be an integer.
No, ma'am, because it is actually a quadratic equation, right? L square plus L equals to K into K plus 1. So
Yes.
there will always be two solutions of L which will give, I mean, K into K plus 1 essentially.
Yeah, but they will always be integers. I mean, can you imagine a non-integer L where L into L plus 1 will give you an integer value?
I mean, I cannot imagine it, but I'm just saying.
I think it is not possible. You can try.
Okay, okay.
It is possible. I think it is not possible because if L is not an integer, then L plus 1 is also not an integer. And if you multiply a non-integer with a non-integer, I don't think you can get an integer. Maybe if it's minus half, can you? Maybe minus half is half into half. No, I don't think it's possible. If you come up with a contradiction, then let me know. Then I'll think
Okay,
about
ma'am.
it again. Okay. Okay, so this is a very important thing which was not obvious to us at any point. That L square only has integer eigenvalues. Okay. And okay, one more point, similar to the harmonic oscillator. So now, for a given value of L, if the odd part of the solution truncates, then the even part will, by construction, not truncate, because that will have a different value of because the k ranges will only go over the odd numbers. So if L is an even number, then only the even solution will truncate, and if L is an odd number, then only the odd part will truncate. So the linear combination of the odd and even, which was a general solution to the Legendre equation, that is not valid for our physical system. So the other point is that if odd series truncates, okay, I'll write it a little bit better. So if L is odd, it implies that odd series truncates, then even series will not, okay, and vice versa. Therefore, wave function solutions are either odd or even, not linear combinations. This This is similar to the argument in the harmonic oscillator. So where are we? Fine. This is the thing. And then let's see. Let's use the recursion relation and verify all the things that we were talking about the Legendre polynomial. So let me go back to the Legendre polynomials. Our recursion relation is this one. So ak plus 2 by ak is equal to minus of L into L plus 1 minus k into k plus 1 by k plus 1 into k plus 2. Okay. And we were told that so this recursion relation will give you unnormalized Legendre polynomials. Okay. So those are the y's that I had written before. So let's pick a y which we will verify. Where is my y? Here. Okay, let's try this one. So this is for so here what are the, so this is then a0, okay, and minus 3 is a2, and this belongs to then y. So this is for n equal to then 2, because there are two terms, 0 and 2, so up to x squared. Let's see. So we have y. So don't confuse this with, okay, I'll put n equal to 2 then. Y n equal to 2 is equal to 1 minus 3x squared, according to the Legendre solutions. This is a0, this is a2, and or if I want to write in terms of L, then L. So a0 is equal to 1. This is given. This I have to assume because a0 and a1 are arbitrary polynomials and they have been set to 1 before we start solving the remaining factors or the remaining coefficients. a0 is equal to 1 is given. So then a2 is equal to,
Ma'am, what are we taking the value of k?
k equal to 0 because I want to find out a2. a0 equal to 1 is given. I want to find out a2. And I want to verify that a2 is equal to minus 3. This is what I want to do from the recursion relation. So a2 is equal to then 2 into 2 plus 1 minus. So a2 is accompanying the second power, the quadratic power of x. So k is equal to
0, right?
Sorry, say k is equal to 0. Sorry, here k is just 0. Yeah, because I've taken k 0. And here I have 1 into 2. So this is minus 6 by 2, which is minus 3. So that's fine. So even if, so here we verified, but if I told you find y for L equal to 2, you would be able to do this and find out what y is for L equal to 2. So let's find out, let's see another one. Find y for L equal to 3. So for L equal to 3, we have to start with A1, which is also 1. This is given or known or whatever. And again, my k is then now 1. And ak plus 2 is then 3. This is equal to 3 into 3 plus 1 minus 1 into 1 plus 1 I k plus 1, which is 2, k plus 2, which is 3, minus of 4, so 12, 12 minus 2, 10 by, so this is minus 5 by 3. My y L equal to 3 should be x minus 5 by 3 x cubed. So let's verify if that is the case. I had written this step somewhere. Okay, yeah. So it is x minus 5 by 3x. So this is how you get the unnormalized one. And then to get a normalized one, if I want to normalize, then I have to divide by 2 by, what was it? 2 by 2 plus 1. So 2 by 2l plus 1, that is equal to 2 by, L is here 3, so 6 plus 1, 7. Did I do this right? Bit of a funny value. 2 by 7. And if I multiply with 2 by 7, then I have x equal to 1. So 1 minus 5 by 3 minus 1 by 3. No, that does not seem to be the right answer. So the normalized one for L equal to 3. Oh, I don't have that. L equal to 3, it should be 2 to the power 3, that's 8. 8 into 6. Okay, maybe it's like that, I don't know. Okay, so let me just see 1 second. So this is this, then this could be the normalization for L equal to 5 actually. So here my L, this should probably be 2L minus 1 according to, so the first one, if L is equal to 0, yeah, so sorry, so this normalization condition corresponding to the convention that I have taken is actually 2L minus 1. So let me just correct that. So which means that this is 2 into 3, 6, 6 minus 1, 5. Yeah, so this actually, it's a convention and I messed up the conventions a little bit. So wait, where did I write this normalization condition? Yeah. So if you're starting from zero, if you're starting from 0, then it is plus 1. No. If it's 0, then I should have
Ma'am, what is the
n
n
equal
then?
to 1. 1 minute. So actually this formula depends on whether you started with the Legendre equation as n into n plus 1 or n into n minus 1, and what your range of n is. Okay. So so everything has to be consistent for the formulae to work out. So if I'm
Is
starting
it n or
from
is it
n,
L?
well, whatever you want. I mean, here I wrote n. So here I wrote n. That's why I wrote n here. But, okay, 1 minute. So if I take n into n plus 1, then my first one is n equal to 0, I guess. So then it should be plus 1. That is correct, right? So this is 0, and this is 2. One minute, let me just verify how they've written the Legendre equation convention. Okay, so this was L into L plus 1, and then plus 1. What is the range of n over here? If I want to normalize it, okay, let's just stop with the normalization once. I will, let's show the Rodriguez formula, and then I'll come back to the normalization. I didn't try out the normalization, of course. Anyway, so this is x minus 5 by 3x cubed. So for x equal to 1, okay, let me just do one last try. Is equal to 3, that is 1 minus 5 by 3. So this is minus 2 by 3. So if you want this, if I want this to be 1, then it should be minus 3 by 2, my normalization factor. Right. So let's just look. So Legendre, polynomials. Okay, and I want 3. So the value of 3 is, so the answer is basically half of 5x cubed minus 3x. So here if x is equal to 1, yeah, that follows. So if I take now 3 outside, then I have, or my, yeah, let's take minus 3 outside, then I have x minus 5 by 3x cubed. Yeah, so then, so if I apply just directly the condition that my PL1 should be equal to 1, then that carries through. So if that, so I get minus 2 by 3, then my normalization factor is minus 3 by 2. So that is fine. So this expression is correct. But the general formula for normalization, that is somehow a little bit inconsistent. The 2 by 2n plus 1. I'll have a look. I think it has to do something with the corresponding form in which the Legendre equation was taken. So I'll check that for you. Okay. But fine. But this is also quite a simple way of doing it, I guess. So, so the condition is that when x is equal to 1, the value of this polynomial should be 1. So you can substitute x and see what comes and then multiply it with the reciprocal. And you get the answer. Okay. The other thing we will do is we will verify the Rodriguez formula. So verify Rodriguez formula for, let's say, okay, let's do it for P2. So what was the formula for the Rodriguez formula? That is equal to 1 by 2 to the power L, so 2 to the power 2, then L factorial, so that's 2 factorial, then the derivative, then to the power L, so 2 times, and x square minus 1, derivative to the power L, so that's 2. So this is equal to then 1 by 8. Dx square of, okay, we'll do 1 ddx already. So if I do ddx of this, then I have 2 into x square minus 1 into 2x. Okay. So 8 can be 2. And then half. Dx of this is x square minus 1 plus x into 2x. That is equal to half of 3x square minus 1. And this is also what we got from the recursion formula. Right? Yes. 1 minus 3x square, and we also get, oh sorry, we got this one. So this is again the normalized form, remember, the Rodriguez formula. So let's try to see if we normalize 1 minus 3x square, what happens. lies y L equal to 2x, which is equal to 1 minus 3x squared. So what I want is y of 1 is equal to 1. Therefore, I have to.
Shouldn't normalization be with respect to an integral? Like, why are we just taking one value, p of 1 equal to 1?
This is the way the mathematicians normalized it originally, and to stick with those definitions, we continue with this. And the overall normalization we will do only when we do a physical system.
Okay, so this is a different normalization than the actual wave function normalization you're saying.
Yeah, this is a different normalization. So I am just showing you this because if I just give you these polynomials, this is how I was taught, but then you never know why you see different expressions sometimes in one book and in the other. So just be aware that there is an unnormalized form of the Legendre polynomial, there is a normalized form. And different books and different authors will take different versions of it. Okay. So just so that you don't get confused, I'm working this out for the moment. This is not so important for the actual physical system. After we solve the radial equation and get the full wave function, only then we can normalize it anyway. This has nothing to do with the physical system as yet. I mean, it's just the L square operator, which is applicable to all systems. Okay, so therefore we need to multiply. So my y for 1 is equal to 1 minus 3, that's minus 2. So I need to multiply with minus half. So that is minus half means I can say half 3x squared minus 1. Okay. So then this and this are the same once I normalize it. So I think I will, just one last thing. There is another expression which gives you directly the polynomial. So in the Rodriguez formula, you have to actually do a derivative and figure out everything. So there is an even more direct formula. So this is, what should I say? A direct formula for Legendre polynomials. Not very useful because it's difficult to remember, but just for completeness. Or I can say L if you like. There's a sum from R equal to 2. And this also covers like both odd and even ones. So this is just one formula. R 2n minus 2r factorial by r factorial n minus r factorial n minus 2r factorial x to the power n minus 2r. Okay, and n by 2. So you see I've written it with a square bracket, so it has a different meaning.
It's a floor function, right?
Yeah, I guess that is what it's called. Denotes it's the greatest integer that is less than this n by 2 number. So this is a standard notation. I did not know that. Okay, denotes the greatest integer that is less than equal to n by 2. So if it is so if n is an or here I've written L again. Oh, I need to change all the N's to L's. That is the problem when the formula is difficult and you're copying from somewhere. Okay. 2L, 2L, this is L, this is L. I hope all the N's are now L's. X to the power L. Did I get all the N's? Let's see. PL to the power L. This is L. This is L. Okay, yeah. So if it is a even L, then the sum will go up to that number. If it is an odd L, then it will only go up to the number before, L by 2. This is it. So this is the direct formula, where you don't have to take any derivatives or whatever. This is useful, for example, if you are doing a code. If you want to code your Legendre polynomial for whatever reason, then this expression would be useful. Otherwise, I don't think it's a very useful formula.
Ma'am,
Yeah.
can you please go to that question where the associated Legendre polynomials are derived, with power series?
I have not derived the associated Legendre polynomials yet, but these are just, it's still everything for m equal to
Yes,
0.
ma'am. This cutting down and yes, that portion. I am saying that portion. Just some. Okay, ma'am.
So what you're calling associated Legendre polynomials, that will come when m is not equal to 0. So far, it's m equal to 0.
Yes, sir. Actually, I just.
Yeah, okay. No problem. Do you all do this in your some mathematics course or physics course?
Ma'am, this was supposed to be done in, I think, mathematical methods course last semester, but the entire power series portion was skipped because of the cut semester.
Oh, okay. But everyone does it?
In the first year, it was supposed to be for everyone, but like I said, it was cut.
Okay. Well, that is good to know. Then maybe next semester I don't need to do so much detail. And what about, do you all have a quantum physics course, some of you, or no? This is the only quantum course.
Next semester, ma'am.
Oh, next semester. So I guess you will have some repeat with this one. Then. So you can let the professor know if you have already covered something. So one thing I did not cover, for example, which I am also skipping because of time, is rigid rotor. So if some of you are interested in quantum physics or chemistry, then maybe you can ask the next professor that please don't skip it. Okay, so I will stop here. There's no point starting a big section right now. So Thursday we'll hopefully do the associated Legendre polynomials, and after that Professor Pal will take over, and he will, if something is left, he will complete it. Otherwise, he will do problems. So as you requested that you want to do problems, he will will solve problems for the whole syllabus. Also, I wanted, so we've only had one quiz, which is not good. We should have another one at some point. So maybe first week of November, we can have a short quiz. And I had planned on end of this month, but that does not seem to be possible. There's too few days left. So maybe 4th of November, Thursday, class hours.
Ma'am, 4th of November is Diwali, so that is
Oh,
a
4th
holiday.
of November is Diwali. Oh, so we missed that. So we need to do one more quiz. Then,
Can you give a 2 weeks notice at least?
so 11th,
I mean, 11th is Friday. Oh,
Thursday.
Okay, ma'am.
Yeah.
ma'am, can it be the twist? I mean, that Tuesday?
That Tuesday, 9th. So Tuesday, usually, you know what happens if we do a quiz, we lose full 2 hours eventually because everything takes so much time. So I prefer
Ma'am,
Thursday.
please not on a Tuesday. We already have an exam on Wednesday, Earth Science students.
Okay, you have an exam on Wednesday. Okay.
Yes, ma'am.
Okay, so I'll talk to Professor Pal. So this is not, so 9th, that means 9th. So 9th is not final, but I'll talk to him and then because he will take it. Okay. I will not be available in November. So he will take
Ma'am,
it.
and just one
A little
request.
later.
Ma'am, just another request from my side that both the class test and the mid semester was not, I mean, time appropriate actually. I mean, both of them required much more time than was given to us.
The
Can
mid,
you
but I
please
think
keep
the
that
mid
in mind?
semester was pretty. Your mid semester
Uh,
you also found too long. That is a bit.
yes,
I
yes,
mean,
ma'am.
okay, so mid semester I tried to keep quite short actually for 1.5 hours.
Ma'am, some questions were very simple and straightforward, but some questions
There was
required too
one
much
question
time.
I agree that there was one question which was quite long. Yes, I agree. I didn't realize it would require so much effort, but sorry. But the rest I think were fine.
Yes, yes. But
The other
please keep
option is,
that.
of course, that after you do all the tutorials, maybe you can give a quiz 16th of November, just before you close. Like the
Ma'am,
last
actually,
day of
for the Earth Science students, that will be helpful because, ma'am, we already have an exam on 10th. And we even have the term paper submissions and those things.
So the last day is better, 16th of November. That's a Tuesday. And 17th is last day of class.
Yes, ma'am, I guess, like, ma'am, or we can take a poll, ma'am, if you allow.
Well, I think you have representatives now, at least from all the streams. If you don't have any other exam on the 16th, we'll go with 16th. Okay. Fine. So at least it's not anytime soon. So we have time to decide the final date. Okay, fine. So I'll stop here for today. Stop the recording.